How does the analog color television video signal work? And why do we care, now that everything's digital? Let's get the second question out of the way first. Digital video is a descendant of analog video, so we should learn about how we first started making video pictures. The second point is that the world around us is analog, even though now we capture the pictures we see on digital video. In this video, we'll look at how the NTSC, or National Television System Committee, analog color video system works. That's the television system we were familiar with from the 1940s, up until the widespread implementation of digital television in the 2000s. In the beginning, there was black and white television. To understand how that worked, let's start with the camera. Back in the 1940s, the television camera made pictures using a camera tube. The live scene was focused through a lens onto the face of a photosensitive plate at the front of the tube. That surface was scanned with a stream of electrons, which turned the original brightness and darkness of the scene into a constantly fluctuating voltage. The brighter the image at a particular point in the scene, the more voltage that would be produced by the camera tube. The electron beam was moved left to right and top to bottom to cover the entire surface of the photosensitive plate by two coils of wire around the camera tube. If we apply a voltage to a coil of wire, that coil becomes an electromagnet. Since electron beams are attracted and repelled by magnetic fields, that meant the electron beam could be moved around the plate. The coils of wire were energized with a particular pattern of voltage, though, a sawtooth wave. To achieve horizontal scanning, one set of coils was energized with a sawtooth wave with a frequency of 15,750 Hz. That moved the beam left to right gradually across the screen in about 63 millionths of a second, followed by a quick snap back to the left of the screen to scan the next line. Meanwhile, a second set of coils was fed with another sawtooth wave, with a frequency of only 60 Hz. That forced the electron beam to travel from the top of the screen to the bottom, 60 times a second. So now we had a fluctuating voltage representing all the lightness and darkness in a scene, and the scanning process was repeated over and over 30 times a second. The camera signal was sent to the television monitor. The monitor was a CRT, or cathode ray tube. It created its own electron beam, which was modulated, or changed, by the original voltage from the camera. The more voltage that was applied to a positively charged grid within the picture tube, the more electrons would be in the stream at a particular moment in time. This electron beam was accelerated and pushed towards the front of the CRT towards a phosphorescent screen, which glowed brighter and darker depending on how many electrons were being sent to it. That created a dot on the screen, flickering with intensity that mirrored the original scene's brightness. The CRT had to then move the electron beam around to recreate the original picture frame. This was done using two coils of wire around the neck of the CRT. The camera has to tell the monitor where there is a dark or light portion of a picture, but it also has to tell the monitor when to start and stop producing each line of video, and also when to begin and end each field as well. That's the purpose of synchronizing signals. A group of special signals are sent by the camera to pass along this synchronizing information. Once a line of picture information has been sent by the camera, the video falls below 7.5 units to 0 units, well below the level of the darkest portion of the picture content. This tells the monitor to stop displaying video information to the viewer, and is called the blanking signal. It blanks out the picture content. To ensure that our picture monitor scanning doesn't drift off frequency over a long time, which would skew our picture in unpredictable ways, we send, in the middle of the horizontal blanking period, a horizontal sync pulse. This gives the monitor a reminder to resynchronize with the camera scanning at the end of every line. This sync pulse is at a level where it can be easily detected by the monitor, and will never be seen by the viewer, at -40 units on our video scale. The pulses will be sent 15,750 times a second, one for each line of video. A similar process occurs with the vertical sweep from top to bottom. During the vertical blanking period, a vertical sync pulse is created. This pulse tells the monitor to move its electron beam back to the top of the screen. The shape of the vertical sync pulse is actually 6 small pulses. It's made up this way to provide continuous synchronization for the horizontal scanning system of the monitor, even during the vertical retrace period. In addition to the vertical sync pulse, another group of pulses is required when using interlaced scanning. Interlacing occurs because the second field of scanning starts half a line's distance across the screen relative to the first field. The analog television system has 525 total lines per frame. Therefore, each field has half that many, or 262 and a half. Since 525 doesn't divide evenly by 2, this means that one field must begin 1/2 line later than the other one. To make this rather complex process happen successfully, we put into the vertical interval signal one group of 6 equalizing pulses just before the vertical sync pulse, and a second group of equalizing pulses just after the vertical sync pulse. Basically, the equalizing pulses make sure that interlacing happens properly, and starts the scanning at the proper points in each of the 2 video fields. Color television. Color television employs the basic principles of black and white television scanning. The essential difference is that a color picture is like 3 pictures in one. The 3 electrical signals that control the respective channels in the picture monitor are produced in the color television camera by 3 CCD, or charge-coupled device, integrated circuit chips. The camera has a single lens, behind which a set of prisms, mirrors, and colored filters split up the full color scene into 3 different colored channels: red, green, and blue. These are focused on the 3 CCDs. These 3 electrical signals produced by the camera are transmitted to the television monitor, where the scene is recreated. Chemical compounds, or phosphors, that convert electron beam energy into light of the additive primary colors, red, green, and blue, are deposited on the interface of the glass picture tube in precise arrangements of stripes of alternating colors. If you look at the screen of a color picture tube monitor through a magnifying glass, you can see that it's made up of many tiny line segment clusters that glow with red, green, and blue light. At the rear of the picture tube are 3 electron guns. These beams contain the picture information for the color channels. These hit the colored stripe segments, and the tube is designed so that each beam can only hit segments of its own color. A shadow mask prevents each beam from striking the other's stripes. Because the colored segments are so small and so close together, the effect, when viewed from a distance, is of 3 superimposed images in the primary colors. Color encoding. A process known as color encoding allows us to send 3 channels of color information down one cable or one television transmission. To add color information to our black and white video system, we utilize a particular high frequency, mix it with the black and white signal, and use it to transmit color information. That frequency is called color subcarrier. Here's how it contains all of the color information in a TV picture. Color subcarrier needs to be manipulated in some way to represent elements of color. What the actual color is, for example, red, orange, yellow, green, blue, violet, and so on, and how much color there is at a particular point in the scene, for example, vivid or pastel, which we refer to as saturated or desaturated. Depending on what color is present in the video signal at any particular moment in time, we adjust the color subcarrier to be a certain phase. Every possible hue has a particular phase of subcarrier. The intensity of the color is proportional to the amplitude of the subcarrier. A high amplitude results in a saturated color. If the subcarrier has no amplitude at all, the video signal at that moment has no color at all. It's black, white, or a shade of gray. Through this process, we are able to produce all of the possible hues we would ever want to reproduce, and also information about how saturated the colors are. There is also a separate reference signal called color burst that is added to the beginning of each video line, just after the horizontal sync signal, but still during the horizontal blanking interval. This is a short blip of color subcarrier, and is used as a reference to give the color monitor a starting point with regard to which color hue is supposed to be represented and how saturated that color is along the line of video. The inventors of the analog color television system decided that color burst would be sent at 180 degrees of phase. So that's basically how analog video works. From the generation of voltages in the camera tube, depending how light and dark the image is at a particular point in time, to horizontal and vertical synchronization signals, to how we are able to add color to the black and white signal that lets us watch full color pictures at home while still remaining compatible with all the black and white television sets that are still out there.